All right.
Yours, please go ahead.
Okay. For those of you that don't know me, I'm Ken Sible. I'm going to briefly talk about NerpyLaTeX today, which is a Python package for converting LaTeX input to SymPy, which is a computer algebra system backend that we use. It's a free open source package available for Python. And all of our parsing that we do in LaTeX fully supports Einstein notation and other conventions of general relativity. So to get started, the package is fully pip installable. So you could just run pip install NerpyLaTeX and grab it, or go ahead to our GitHub repo. So there's two ways to interact with NerpyLaTeX. One is, say, inside of a Python script. In that case, you'll just import this parse LaTeX function. So you see I've highlighted this line. The highlight doesn't show up particularly well, but just from parse LaTeX, from NerpyLaTeX, import parse LaTeX. The other way is if you're in an IPython or Jupyter environment, we actually have an extension that supports line and cell magics. So you just do this load extension NerpyLaTeX.extension. So I'm going to use both of those in the notebook today and show you sort of the advantages and disadvantages of each. So our design philosophy here is that the philosophy for learning NerpyLaTeX is sort of not to dig through tedious documentation, to sort of jump in with examples, work through it. We implemented sort of a nice, robust error handling system in the back end that hopefully gives you good feedback. I recently put in a debugger, which I'll show off today. And so the idea is just look through these examples and try to write some of your own code, and then hopefully NerpyLaTeX will guide you along the right direction. So instead of talking about a bunch of logistics, I'm just going to start with the first example, which is the Schwarzschild solution to Einstein's equations. So we're going to do this in a Jupyter environment first. So I have this parse LaTeX cell magic, which tells it to take the entire input cell, which is just filled with LaTeX code, and pass that to NerpyLaTeX. Also, it renders the LaTeX output. So you can see at the bottom of the cell what you put into it. So you could technically take this code, and maybe you had it inside of a paper, and so you could have this, rendered, these equations fully rendered in your paper. You could annotate everything in LaTeX comments, and then tell people, hey, you could go download the source code for my paper, and then just pass it into NerpyLaTeX and run it, which is part of our design philosophy here. So this example is fully analytic. To get started, we're going to define our coordinate system. So you use this coord command. And so for the Schwarzschild coordinates, you have tr, theta, and phi. And all of our commands are just, again, they're embedded inside of LaTeX comments. So you have a single % coord, and then you define the system. If you do a double %, that tells NerpyLaTeX to ignore that line. So it's just a NerpyLaTeX comment. The second line, we define any relevant constants. So here we define G and M. And you use this define command, and you have this const flag at the end that tells NerpyLaTeX, this is a scalar, ignore it, and any derivatives, it has no dependencies on any other variables. And so when we declare the metric, we do that in several steps here because we're doing this calculation analytically. The first one is we want to just basically build a matrix of zeros, and then we're going to specify the entire diagonal, and then tell NerpyLaTeX, hey, this tensor is a metric. Please go ahead and compute the inverse determinant and all associated Christoffel symbols. So to get started, we do define. GDD is the convention, the naming convention that's used in NerpY+. So DD tells you that it's rank 2 and it's both covariant. Both the indices are covariant. You say it's dimension 4, and then the 0 flag just says fill it with zeros. And if anybody has any questions along the way, feel free to stop me. So the next part, we just define all 4 of the diagonal components. You'll notice all of these are inside of comments so that they don't render in LaTeX, but because it's only a single comment and not a double comment, NerpyLaTeX will still parse all of those. So that's the way to still parse calculations that you need for later, and you can embed those in, say, your paper source, but they're not rendered. Another thing to note, you'll notice I index all of these using the coordinates I defined above. I put a little comment here. Of course, you could do it numerically going 0 through 3, or you could use your coordinate system if you specified one. And the right-hand sides are just LaTeX mathematics, and they'll be parsed to SymPy. Okay. And the last step, we have this assign command, which essentially
Why do you need to do a line break at the end of the assignment?
These line breaks here at the end of all the components.
Yes.
But that's just so that there's line breaks in the rendered output. It's not anything for parsing NerpyLaTeX. You don't need them.
Oh, okay.
Yeah.
Cool.
I will say this. So if they didn't have these comments here, like if I had these two equations and I chose not to put this line break though, NerpyLaTeX will get confused because it ignores white space typically. So it'll just assume this is one long line and that these two are multiplied together, and then it's going to see another equal and get confused.
Okay.
But usually, again, the error handling and the output's going to point all that stuff out to you, and it'll tell you that you kind of need to find a way to separate those two equations. So it'll be clear, but mostly it's just for the rendering. Okay, so this assign command allows you to take any of the options that you would normally have in the define command and put them onto a variable that already exists in your namespace. So here we already have GDD. We've been working with it. I'm using this metric flag to tell it, hey, this is a metric. So it keeps track of that because in NerpyLaTeX, you can use multiple metrics. So it just adds that to a dictionary in the back end, and then it generates the inverse determinant and any of the Christoffel symbols for you. Okay. So now we have our metric, we have our constants, we have our coordinate system defined. So here we have all of the equations we're going to be parsing, and I put them inside of an align environment. So this is an example where begin and end a line are commands that NerpyLaTeX doesn't know, and it would flag those as unknown if you tried to run it. So we have this ignore command where you just pass in strings and say, please ignore these during parsing. So I tell it to ignore the begin and end line tags. It'd also be useful, for example, down here with the definition of the Riemann tensor, you maybe want to put Q quad here and put a line break and just do some formatting. And then it'd be useful to go up here and just say, hey, ignore that sort of formatting space command, right? So you could do any of that type of stuff. So any other commands you use, you need to ignore. You just use that ignore command. And then, so for all these tensors, the Riemann tensor, Ricci tensor, Ricci scalar, Einstein tensor, Kretschmann scalar, I've defined them all with their appropriate definitions in LaTeX, and NerpyLaTeX will just handle and parse it fine and do those calculations for you. One last thing I wanted to note here on this last equation, I do this contraction over all components of the Riemann tensor, but you'll notice I only defined using the NerpyLaTeX notation RUDDD, but down here, I use on the right-hand side RUUUU and RDDDD. So Nerpy already knows that this metric GDD is associated with all these tensors I defined, and it can do automatic index raising and lowering for you, so you don't have to waste time with those internal calculations. So by default, every tensor is assumed to be associated with the metric G. And you'll see later when I talk about multiple metrics how you can change that default association. So for right now, it does a lot of assumptions that are just conventional to general relativity. Like another one just to mention, all of these Greek indices are assumed to be 4D, and all Latin indices are assumed to be 3D. And of course, you can change all that. And then finally, just to demonstrate this works, I import the simplify function from SymPy. You see that this K is already injected into my Python global scope, and I could just use it. And I call simplify, and you get the correct output for the Kretschmann scalar for the Schwarzschild coordinates. So if there's no questions there, that's my analytic example.
I have a question, sorry.
Yeah.
Where did you tell the code that R is the Ricci tensor? I mean, responding to the metric, or we can...
Yeah, I just have these three definitions here, and I just put in the right-hand sides in LaTeX.
That's going to generate Nerpy tensor or Nerpy index objects.
Yeah, so in this example, the next example I'm going to show is meant to be passed to NerpY Plus for numerical workflows. This first example, right, is entirely analytic. So I'm defining the metric in terms of my coordinate systems, and all the tensors I define down here and their derivatives are dependent on the metric, and so everything is just kept completely analytic throughout. So
when you tell that GDD is a metric, it already computes the inverse metric, the determinant, and all the Christoffel symbols that it can. And that's why when you write, you know, if you look at the LaTeX route down there, you're writing the Riemann tensor, and that only depends on things you already know.
I have to call my Christoffel symbol gamma.
Yeah, it has already computed when you said the GDD is a metric.
Well, I want a different name, maybe a funny name for my
Oh,
symbol.
in that case, I think you would need to, if you want to change the name of the gammas, can you do that?
Yeah, well, what you'd have to do then is when you go up here after you do assign metric and it generates that, I mean, you could do whatever. If I wanted to do B,
Yes.
right, then you just have to, I'm not going to tell you about the whole thing, right? But you could just reassign to something else if you want to change it. And of course, you probably want to put that in a comment so it's not rendered, right?
So, Ken, if you wanted to, you gave us a simplification for K. What if you wanted to get the simplified version of GTT, capital GTT?
I'm not sure what you're asking me.
Hold down.
Oh, you mean line sentence or?
Yes.
Yeah, so you have simplify K, right? I want to see the simplification of GTT, the Einstein tensor.
You just want me to contract over its indices and just get the scalar version of it?
No. The capital G that you define just above the K is Einstein tensor.
Yes.
To the TT component of that one.
Yeah, I want to get the TT component of that one and simplify it.
I think I remember what you're saying now. It's been many years at this point since I've done general relativity, so I honestly don't know off the top of my head what that means anymore. That's trace something.
No, not a trace.
Is that what we're talking about? I don't
the object
remember.
G now. You have the object G.
So why don't you just put in G? So in your input 3, why don't you just put in simplify capital G TT and see what it does?
GDD
Right.
00.
We
just wants to look at that.
We want one component of the Einstein tensor.
The fourth equation.
Yeah.
Yeah.
That one. He wants to look at the 00 component of that and ask you to simplify it.
Just one component.
Oh, okay.
Just to see another example,
Yes.
which is maybe a little bit more
Exactly.
complicated.
Okay, it should be 0. Yes.
But you can verify that it is.
Okay, and so is there an RDDDD? Is that defined also?
I don't think so, right?
4Ds.
Yeah, that's defined. Yeah, because whenever you called this on the right hand side, it computed that on the back end, and so you have access to it.
Okay.
All that stuff's great. I will show later. Maybe I'll just scroll down now. If you use the parse LaTeX function instead of the cell magic, you actually get as output. It shows you everything that was created for you. But because we're in a Jupyter environment, it shows you the rendered LaTeX instead.
Right. Okay.
So you would see all those variables that are created that you did yourself and those that were created implicitly for you.
Okay.
Yeah, I apologize for that. I thought you were saying GTT and not DD, and I was getting confused.
Oh, GTT, okay. I meant G00. I was using your coordinates.
Yeah. Sorry. It's difficult to hear, but yeah.
So I have another question, and maybe I missed the beginning, so I apologize when you already, if you already said that. Can you also do manipulations without specifying a metric? So say I wanted to do some really abstract index calculation using NerpyLaTeX. So I'm just thinking about, I'm going to give this extensor tutorial next week, and the whole question came up again, do we have anything that's similar, but for open source? Because some people may not have access to Mathematica. So how powerful is this one?
You mean just keeping the metric generic?
Yeah, so that's the next example I'll move on to. Here, I don't do anything analytic. Everything is kept generic. I also say that, and I should have said this at the beginning, so on our GitHub repo that I pulled up here, if you click this launch binder button, you have access to this interactive Jupyter notebook on my binder that I do in the tutorial. But also there's a little bit here that shows you with SymPy how you can convert the output to Mathematica and other things. So yeah, it's nice that you have SymPy because it's free and you don't have to have access to a Mathematica subscription. But I will also say, since it was brought up, that of course SymPy will allow you to convert to other computer algebra systems should you want to work in those instead, but use LaTeX as a front end.
Okay, great, thank you.
Yep.
So here's another question, Ken. Suppose I want to have all my GDDs unspecified. I just want them to be, GDD00, GDD01. How would you do that?
You would just do this define command, right? So GDD dim4, something like that.
That's all.
Yeah, and you didn't, nothing was specified. It doesn't have a right-hand side, right? And you just keep it all completely.
Right.
And seeing your command, is everything hard-coded for 4 dimensions, or do you have the flexibility to have any space-time dimension if you want to?
Yeah, so I'm going to show an example below where I do mixed indexing with 4 and 3, and 3 goes over the spatial indices. I have an example entirely in 2D, just calculating Christoffel symbols on a 2 sphere. You could do whatever you want. Yeah.
You don't try higher than 4, but you could try.
That would be another question.
I think she's interested in higher dimensions.
Well, not only.
Yeah. It should support anything.
Great.
So this next example is the Hamiltonian constraint from the BSSN equations for vacuum spacetimes, and it's completely symbolic, no analytic references. It's meant to be used in a numeric workflow and passed to something like NerpyLaTex Plus to generate C kernels for finite differencing. So here again, we do this parse LaTeX. I should have said this before if I didn't. This reset flag just tells it that NerpyLaTeX keeps a track of all the variables you created in this internal namespace. And so any variables that were created in this last cell I ran would normally be accessible in this cell. But because I don't want any conflicts and these two have nothing to do with each other, this reset tells it to just clear its internal namespace. So that is, you could break down NerpyLaTeX calls into several different calls, say if you were putting them in a Jupyter environment or something, but you wanted all the variables to be accessible to any of the subsequent calls, then that's the default behavior. So this just changes that. So to get started, we're going to define this 3D unspecified metric. And so just ignoring this for a second, this is exactly the same as I've been defining things before. Our metric here is gamma bar DD. And you just put the metric flag that we assigned to that analytic metric before right here. So we haven't specified any of the components. They're completely unspecified. And this tells it to go ahead and compute those unspecified determinant, inverse, Christoffel symbols, etc. This new option deriv using the NerpyLaTeX notation. So if I have gamma bar DD, then the derivative variable is underscore DD. So this just tells it what suffix you want to use.
I have a very quick question. So what's your signature of the metric and where do you define that? Because now the 3-dimensional metric, of course, would be just a plus 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 signature, whereas the one we had before was presumably a minus plus plus.
Yeah, so I was going to say, basically, if I was to, let me not do the derivative here. If I was to query this, right, the Python output is just this SymPy variable. So that's what it looks like when I say unspecified. So then what you would do later is you would have all these calculations, and then you would go through maybe in a for loop over all these components and do like that SymPy variable dot subs each of those components and then replace them. So nothing about this metric is specified right now. You do it later in your numerical workflow.
I see.
But all of that stuff is documented in the main NerpY repository in that tutorial section.
Is it fair to say that there is no signature because it's completely generic?
Yeah.
I think that's.
But you could do what he did before.
You could.
You're right. But if I wanted to keep it general and would rely on having a certain signature in my metric.
Yes, you could specify it later on or something.
That's good.
And so another example is because these derivatives may be computed finite difference. I have stuff like if you do this is the NerpY notation d up d for an upwinded finite difference derivative. And so you could do different derivative suffixes that NerpY then handles on the back end. So in the next case, I need to define these two variables, a bar dd and r bar dd. Those are just 3-dimensionals, same derivative suffix. Here, they're symmetric in the first two components, so you could flip them across that matrix diagonal. And so this sim01 is just NerpY Plus's notation for symmetry. And you just specify the indices that's symmetric with respect to. If you want to do anti-symmetric, you just do anti. Otherwise, yeah.
I think you didn't mention this. This is already like inside the, when you specify that a tensor is a metric, he's also implicitly applying something like this, right?
Yeah, when you do metric, again, inverse, determinant, Christoffel symbols. And in case all those are unspecified, yeah.
It's enforcing the fact that it is a metric or no?
Yeah, it's important that it's a metric. Again, it does two things. Yeah.
When you say metric, it enforces that the metric is symmetric, or no?
Oh, yes, yes, it enforces symmetries. Yeah.
Yes.
And it will tell you, by the way, that if you do this calculation analytically and then try to assign metric like that we did here, if it's not symmetric, it'll give you an error and saying that that can't be a metric. So yeah. And then of course it does it here, forces that symmetry so that, you know, for the sake of memory, that when you go to apply stuff, that it doesn't need to copy things. And I should say that in the main NerpY repository, we have all the BSSN equations parsed in Cartesian coordinates with NerpyLaTeX. If you want to look through those, this is me only picking out one very, very tiny part of it to show here. So you could look at the full thing there. So after we get those two variables we need, we calculate this, this R bar. And I, again, put it inside this comment that it's not meant to be rendered. We parse it internally, so I comment it out. Something else to note here, I define this, this scalar CF. Normally, you wouldn't have to define a scalar. NerpyLaTeX would just use it, and it'd be fine. But because we're going to take a derivative of it, right, if I take the gradient of a scalar, I'm going to get back a vector, which then has a dimension, and the scalar inherently doesn't have a dimension, so NerpyLaTeX doesn't know how to infer that. So I have to actually define a scalar, tell it the derivative type, and then give it a dimension. But if I wasn't taking a derivative, I wouldn't have to define the scalar.
I'm wondering something else. So
Yeah.
we get these rendered outputs if we're in the notebook. Can we get a like GIF or a ping or something if we're not in a notebook?
I see what you're saying. I don't know how to do that. So this notebook rendering, IPython has a package that you can import. And so I think it's like from IPython.display import LaTeX or something, and I import that from them on the back end and use it for the rendering here. So I'm not, you know, the notebook is doing all the rendering in the back end. It actually is returning the LaTeX and then doing so. So I don't know how to grab the PNG or something from that.
Got it.
Okay, so this next part's a little bit tricky. So we have support for this srepl command, which does what I call like syntactic string replacement. Effectively, what it does is it's doing string replacement, but it's doing it in on like the token level. So not with every character. Like this entire /partial is like a character. You can think of it like that. It's one token in the parser. And the point of that is people will do things different. You could have different spacing. I could have a line break here. I could do whatever right in an equation, and it's all going to render the same in LaTeX. So we wanted to keep that behavior here. So that's the way our string replacement works. So there will be cases where you go to do string replacement and maybe the behavior is a little bit different than you expect. But I'll show when I get down to this third section here how the debugger works, and hopefully it'll make sense because you'll be able to see what happens on the inside to your LaTeX whenever you use this srepl. But here in our Hamiltonian constraint, we have several references to this variable phi, which in these BSSN equations we need to get rid of. And we're not going to have any references to phi. We're going to use this conformal factor CF. And so one is this e to the -4 phi is the conformal factor squared. So we tell it to go through this equation and replace every instance of that. You'll notice that I put the CF inside this text command. That's NerpyLaTeX way to make a compound symbol, because if I just did CF, it's going to think that's C times F, and those are two separate scalars. So if you put it in this text, then it's going to group that together as one scalar. And so then I just tell it to do the string replacement. The next line is a string replacement, but I have a capture group. So NerpyLaTeX has support for capture groups. You just put them inside of angle brackets and you number them accordingly. So it's very similar to regex notation. Here, I'm going to replace a partial derivative of phi using phi's definition, which I don't think I put in this notebook, and just expand it with the chain rule in terms of partial derivative with respect to the conformal factor, because I have several partial derivatives with respect to phi that I want to get rid of. What the ... means, it means continuously. So if you just did the angle bracket and one like that, it means capture one token. But it can be difficult because you don't necessarily know what the parser considers to be a token. So if you do the ... it means continuously capture tokens until you see the next thing. So the next thing is phi. So this captures everything that comes up after the underscore to phi, which is just going to be the index for the partial derivative. But what's neat about it is if I just did partial underscore I, that would be fine. But if I did like angle brackets and I wanted to make my indice I naught or something, it'll capture the entire underscore I naught, take it and copy and paste it over here. So that's what the dot dot does. Continuously capture till you see the next token. And there's a whole bunch of these. The sREPL can be confusing, but there's a whole bunch of examples in the main BSSN equations in the NerpyPlus Plus repository and on several notebooks, tutorial notebooks that are linked on our GitHub page. So that's what that does. Now, the thing I will say is this partial derivative occurs inside of the covariant derivative. Now, covariant and Lie derivatives are automatically generated for you with NerpyLaTeX, just like the Christoffel symbol. So you don't have to define those right-hand sides. So here I'm just highlighting an example. I have d bar I of phi. So the covariant derivatives, you could do it with nabla. You could do it with d if it's three-dimensional. You could do it with the semicolon. You could do comma semicolon notation if that's your preference. All of those work just fine. So the thing I did, and it can get a little bit tricky, is there's this persist flag I put at the end, and it tells NerpyLaTeX, just like I said, between subsequent NerpyLaTeX calls, it keeps track of all the variables you created and you can continue using them. Persist means for every subsequent call to NerpyLaTeX, apply this sREPL again. So actually, when you do something like call a covariant derivative of a variable and it expands the right-hand side, it recursively calls parse LaTeX again. And so if I do this persist, it applies this sREPL internally. So you see none of that. So it could be even more convenient, I guess, if you just wanted to take this variable for the covariant derivative, expand it, define it yourself, do this chain rule expansion. Of course, you could do it all yourself. But if you get good at using NerpyLaTeX and this sREPL, you could do a ton of powerful things with it. And when I show the debugger, you'll be able to see sort of what the output happens. Like it'll show you this LaTeX and how it changed after the sREPL. And so you could debug and work your way through trying to get it to have the behavior that you want.
I have a question based on this example. You have a e to the minus 4 phi replacement to text CF squared. Yeah. Is that getting ignored? Because when it gets rendered, I still see e to the minus 4 phi.
No, so when it renders, you don't see any of these replacements, right? Because the idea is this is what the equation may look like, say, for example, when you have it in a paper. But when we actually go to do the calculations with NerpyPlus, Plus, we didn't want to have that phi. We want to use this conformal factor, which I can't remember because I don't work in this area, but it had something to do with how you do the numerical calculations. And so we're changing that stuff on the back end before NerpyLaTeX does calculations. But the rendering in, say, your paper or something, this is what the equation looks like.
Right. Then let me follow up on that, because I would be interested much more in getting the replaced equation, right? So I may have an old textbook where they still have it in this form, whereas a modern version would have the conformal factor in the phi or in the w squared form. So I would want that as output. How would I get it?
I would say if you want it to be output, then instead of doing the sREPL, you would just go and actually just change the equation down here itself. So where,
I have to use something else to compute the equation and then put it in here, or could I take from an old textbook this equation, put it in, and then say, okay, I have this replacement, put it out what it should be now in the new variable?
It doesn't do that right now, but if that's a feature that you want, I could absolutely make it so that there's a way to have it show you after the replacement.
X-tensors precisely to have some of these replacements very easily, right?
Sure.
Yeah.
And
if it's internally, then should be able to output that as well.
Sure. And then the last thing I do is, so we have this d bar squared. I just define that as a custom operator. It's just these two covariant derivatives, and you could just do something like that with sREPL, and then we parse the equation and it works. I don't have validation in this notebook, but it's all validated against hand-typed equations using SymPy in the NerpyPlus Plus main repo. So that's just an example of this numeric workflow. Something I will say, you'll notice that this covariant derivative has this diacritic bar on it, and that's how it knows that it's associated with gamma bar DD. So that's the NerpY notation in a variable form for how you would bar that gamma DD metric. And so because they're both bar, it assumes that association exists. So this is another one of those cases where it makes a couple assumptions for you. And again, I'll show you a little bit later. You can actually make that metric association yourself and say, hey, if I'm taking a covariant derivative of this ADD or whatever, please use this metric instead. But by default, it's going to assume G, and then after that, it's going to try to match diacritics. So if you want to have several metrics, like I could have G bar, G tilde, G hat, whatever, and those are going to go with the appropriate flag tensors, if that makes sense. Okay, so this third section is brief. I'm just going to touch on sort of the exception handling and debugging. It's just 4 really short examples here. Here I have this illegal bound index, so it's going to tell you if to do index checking on Einstein notation, if there's issues there. Unbalanced free index. Here's a parse error. It saw a symbol that it didn't know what it was. Down here, I attempt to parse. Oh, you can see that I could also do, here's the cell magic. Here's like a line magic. If you're familiar with those in Jupyter, you could do either of those. Here I attempt to parse the forecurrent, which is a covariant derivative, but I didn't define a metric, so it doesn't know how to do that, and it tells you.
Could you scroll up a minute? So the cell 5 kind of confuses me a little. I would have thought that you wouldn't need that defined there. I would have thought that what you did is you would define, say, VD instead of. I mean, you've already defined G before, haven't you? So why is that?
It's just an example of something you're starting from scratch.
Oh, that's an example.
Yeah, all my examples in the notebook, I didn't link any of the cells together. I did that reset option and wiped the namespace in every single one of them. But otherwise, yeah, if you already define GD, you don't have to do it again. You just keep using it with every call, if that's what you're doing. Yeah.
You wouldn't have to do that again on the next one because you have to find GUD, but it's assuming that it's starting from scratch again.
Here, I normally would put the reset in all these examples, but I don't have to because they errored out. So nothing was actually saved, but yeah.
Okay, yeah, I guess one of the other things that sort of confused me is I saw the GUD and it was, and then the VD, and that sort of matched the expression on the next line, and I was thinking of it as multiplication, but it's just defining 2 tensors.
Yeah.
That would be the equivalent of the 2 lines, define GUD and define VD.
So you would be very keen, you would put the reset in there.
Yes.
Yeah. And these are just 4 brief examples, but there's a vast number of these error messages I put in. So I think our BSSN tutorial notebook, which is a little bit out of date, so I'll have to find some time to update it. But the idea of that is it's a very long notebook, but we just put in one equation at a time. NerpyLaTeX gives you an error message, and then we attempt to fix it and add in all of these like command annotations based on the error message until everything parses and works, and then we validate it. So the idea is to walk you through that if you just had an equation, that hopefully you wouldn't have to go read a bunch of documentation, that just from the error messages alone, you would be able to build all the correct NerpyLaTeX code. So hopefully it should be intuitive to work with this package.
Is nabla assumed to be the 4-dimensional covariant derivative or no?
Any dimension, depending on what you're using. Yeah. The only one that's specific is D has to be 3-dimensional, just convention. Cool. So the last thing I note is if you do the parse LaTeX function, which you see here in cell 9, instead of any of these cell magics, if there's an error, you'll get the full Python stack trace, which could help with debugging that error message. Or if you do something where you manage to get an error message that I haven't thought of and haven't added something specific for it, right? It might be useful to have the stack trace. So here's an example of the debugger. If you do, I'll say 2 things really quick. If you do the parse LaTeX function, one thing is you have to use this little R to tell Python it's a raw string that escapes all the backslashes and stuff in LaTeX. Now, when you do like a cell magic or something or a line magic, Jupyter escapes all those for you. But if you pass it in a Python script to this function, you have to either escape everything yourself or make it a raw string, which is available in Python 2 or 3. You just add an R. And then all of these flags that I had here, like I don't have it, but -- reset, stuff like that, they're just arguments to parse LaTeX. And so I turn on this debugger with debug true, and you could just do -- debug in an IPython or Jupyter notebook. And so here, just to show you, I'm doing the Lie derivative of this ADD with respect to this vector beta. And everything is just unspecified. And you see the output. It does two computations here, and it shows you, first you have your LaTeX input, and then it shows you the SymPy output that the parser generates, and finally the Python output that NerpyLaTeX generates. And so hopefully it helped with debugging. And here you can see what the full right-hand side expansion of this Lie derivative looks like. Also, I didn't say it, but since we're talking about Lie derivatives, you can go up here and specify the tensor weight, which is important for that. So just so you know, when you're taking Lie derivatives, you can specify that tensor weight. And yeah, so this helps with debugging. You can see the entire right-hand side, and then of course, finally, what the Python code is generated. And then again, if you do parse LaTeX, instead of getting that LaTeX rendered output, you get a list of all the variables that were added to your namespace that then you could just start using. Okay, down here, I just wanted to demonstrate, I copied a similar sRepl long persist thing that happens internally like we did above for that Hamiltonian constraint. And here, just to show you, like if I look at these two differences, let me scroll that just right. So you can see LaTeX input 1 and LaTeX input 1 here. I have this partial derivative with this beta, and this pattern says if I have, some contravariant tensor here followed by a partial derivative, you're going to then, this is there's two of these examples where this happens in NerpyLaTeX. You have these things called like end of line annotations. So I just put this right before my partial derivative, and it tells it that you're going to switch this on the fly. In this particular case, please upwind this partial derivative, change that ending. Note though that like if I was doing that right here in line before this Lie derivative, and I put deriv d up d, I then have to put a line break there because LaTeX doesn't support inline comments, right? But even if I put that line break, this equation is going to render just fine in LaTeX. It means nothing, right? But because that's happening up here internally, I don't have to put that because I don't care how this renders. So you just put this deriv d up in front of your derivative, and it switches that to be whatever type you want, in this case, upwinded. And so you could see here, here I have one instance of that pattern, and down here, I'll highlight it again. I have the other instance, and NerpyLaTeX does that string replacement for me. And so you can see what that output looks like internally to make sure that what you typed in is correct, if that makes sense.
Another question.
Yeah.
So you've shown us this percent define stuff for various things. What if you, is there a way, if I've already defined something, to say use that? So you say define beta u. Suppose I've already defined beta u, and I just want you to use the beta u that I've already defined. Is there a way to do that?
Do you mean like if I had defined, because I defined beta u up here, do I just want to delete this here and just have it use it?
Yes, no, I'm saying, what if I defined beta u outside of NerpyLatex?
Yeah, you could do that. Yeah, it should. I'm trying to remember. I'm pretty sure it can see your Python global scope. And so if you had defined it, say if you just actually compute it with SymPy, right, outside in another cell, you should be able to use it inside the parse LaTeX call. I'm pretty sure that's true, but I do have to double check.
Right.
Yeah. There are some scenarios though where it will cause trouble. So here, when I compute this Lie derivative, this is the notation that we defined in NerpY plus. LD means Lie derivative, and then you have beta as the vector it's done with respect to. So down here, when I do this BDD equals this, I'll just highlight that. You could see it calls that Python list of lists. So if I had defined that elsewhere, of course, it can just use it because that variable was created up here, but I could create it elsewhere. But there are situations where it needs to know what the LaTeX right-hand side is if you, there are situations where when you're taking certain partial derivatives and it has to do the product rule and stuff, it subs in the LaTeX right-hand side, does a bunch of expansion and figures things out for you. And so there's some situations where it might work to do something outside of NerpyLaTeX and it might not. And you just have to see if it works or not and what the error output is.
Okay.
So this last section I have is just a quick survey of just a few features I picked that NerpyLaTeX has, just to demonstrate them. One is I could just do expression parsing. Doesn't have to be an equation, doesn't have to be in anything. I could just parse a SymPy expression. I could do the comma semicolon notation. So here's an example where I use a comma for partial derivative. Semicolon would denote a covariant derivative. So you could do that. Here's an example where I do this mixed dimension indexing. Typically, I think you would do 4 and 3, and 3 would go over the space-time indices. I just did 3 and 2, so this output wasn't super long. But you could see down here, I contract over this I, which is a 2D indice, despite TDD being a 3D tensor. But the one thing, a new command I have to introduce here is this index command, and it allows you to tell NerpyLaTeX, again, Greek indices are assumed to be 4D, all Latin indices are assumed to be 3D, I is a Latin indice, you have to tell it that it's meant to sum over 2 dimensions, not 3. So that's how you change that. And by default, it's going to assume the upper end of dimensions. So in this case, 1 and 2, and not 0 and 1 for the 3D.
Okay. When you say bin 2, I guess that implies that little I will go from 0 to 1. Is there a way that I can make it go from 2 to 3? Those are my angles?
It always goes from 2 to 3 by default. It'll pick the upper end of things. I assume that like if you were doing 4D and 3D, if your first 4D indice was meant to be time, you're probably contracting or doing something over the spatial dimensions. And so it always assumes the upper end. I haven't run into any scenarios where somebody wanted to do it so that it did over the lower end. So I don't have support for that to be able to flip that. But if that's something what people need, I'd happily make it so that you could choose whatever.
That's not what you're doing there, right? VD is going from 0 to 1.
Is it?
Yeah, if you look at your output, then yes.
Yeah,
Oh, it is. I don't know. I've never tried it with 2 and 3 dimensions. I know it works with 3 and 4, so I'll have to take a look at that. But it's supposed to do the upper end. But yeah,
using the Nerpy convention where we normally start everything from 0, and then it's the programmer's job to figure out which is.
I mean, is there a way to define which dimensions you want to then sum over? So I could see the example, right? So I can see the example that you, I think, had in mind where you sum over 2 angles, 2 spatial indices. But I could also see an example where I say I'm interested in the spherical symmetric space-time that's time dependent. So I would have T and R, so 0 and 1.
Yeah.
And is there a way to specify that as a end user?
I will add that. That'll be something I work on this week. I decided to just use this dimension thing. I don't know, because I was playing around with it this week and I changed how this index command worked, and I must have flipped it because it's doing 0, 1, and 2, and it was supposed to pick the upper end of things and it doesn't. But I did have somebody ask me if we could make it so that it was more like you specified, where is it? Let me back this out. If you specified a range or something like that, and you could be like, or whatever. If there was something that was more, I'll work on changing that so that you could change it to what you need.
Misunderstandings, or make sure that people really put in what they think they put in.
Right.
Both will happen, right? So I did self-force, and you might split something straight to symmetric of the angles, the upper one, and then you might have T and R, the non-angle ones that you sometimes also want to sum over because they're scalars with respect to the angular metric.
That's right, that's right. Yeah, and if you're thinking about the 3+1 split, then yes, your 2-dimensional metric will be the spatial metric, but it may not be. So, yeah.
Yes, so I'll work on that. This next example is computing some of the things we were talking about before, but on a 2-sphere. And what I was trying to demonstrate here again is this index command. So because everything's in 2D, I have to change all the Latin indices to be 2D. And so you could use this like regex notation. I put it in these angle brackets and I say all A to Z change it to dim2, and then down here I print off one component of the Christoffel symbols and one component of the Ricci scalar, just to check that everything was calculated correctly. So that's all I have to say about that. You could change that index loop summation range. Here, you can actually disable the implied summation by putting at the end of an equation this no imp sum annotation, similar to how we did that deriv dd inline annotation. So just to briefly touch on this example, I define my coordinate system. I define this gamma hat dd. I define this rdd, and I want to set the diagonal of this gamma hat dd to be the diagonal of rdd, which I can't do with Einstein notation, but I can if I turn off this implied summation. And then down here in this calculation, there's actually a Hadamard product, which again, I can't do with Einstein notation, but I can do if I turn off the implied summation. So hopefully that makes sense. And then in this example, these last two examples here, I talk about how you do multiple metrics. So the first one I'm going to touch on, that sort of what the metric inference system is and how it chooses a metric if you don't tell it. So here I define two metrics, GDD and G hat DD. And down here, I take this covariant derivative of this tensor F, but I put a hat on the covariant derivative symbol. And so it assumes that goes with G hat DD, which if you look at the output, you can see that is in fact what it did. I could also, if I want to, it'll make that assumption if I put that hat on F. So if you put those diacritics where appropriate, it makes certain assumptions about the metric. But at the same time, say I come down here and I just wanted to declare a metric HDD, no diacritic, no nothing. And I want F to go with HDD. I do that dash metric option on F, which would normally tell it, hey, F is a metric. But if you pass it an argument in case HDD, it says, oh, HDD is the metric associated with F. So then if I come down here, you'll see it's taking derivatives of HDD and stuff like that. And it is in fact using HDD when it computes the covariant derivative. So that's how you would assign a metric if you're not just going to use that diacritic inference system. So if there's any other questions, that's all I had.
Are you on Skype?
I'm not on Skype, but I could make a Skype.
I just I'm going to try to figure out how to use some of these features in possibly ways that break things. I just want to I want to be able to bug you.
Yeah, well, if you, I'll type it out here so you can see it. So my email is just ksible@nd.edu. If you shoot me an email or something like that, I could make a Skype account. I could hop on Skype or a Zoom call or something if you need me.
All right.
Yeah.
Let me just write that down somewhere.
Okay. So, any questions for Ken? Steve is the next speaker, so while he's typing, nothing else will happen.
Well, I want a bathroom break, of course.
Okay, but even longer, nothing will happen. Alex has a question.
Well, I think we should second Ken. This was a really great presentation. Thank you.
Yeah, thank you.
Thank you.
Oh yeah.
I would have a question. So there's only one thing left to convince me to move to NerpyLaTeX instead of using exact in Mathematica. Can we do variational derivatives with Nerpy?
What type of derivatives?
Well, say I want to variate an action with respect to some field. Variational derivatives.
I'm not familiar with that, so I'd have to, if it's not something we have, and I don't think we have it, then it could be something that I could add if you want to use it, but I'll have to go read up on it.
Yeah, so basically you would take a Lagrange and you would minimize the action.
Exactly.
So take a derivative of that with respect to a field. So think of it having a Lagrange derives equations of motion from that Lagrange.
Yeah. Yep.
Yes. Yeah, it's I'll make a note of that and I'll look into it.
Yeah, I think we currently support covariant derivatives, Lie derivatives, partial derivatives,
yeah.
And many combinations thereof when it comes to whether you want to do it symbolically or whether you want to do the DD notation, if you will. So totally generically, meant for numerical use. But yeah, more derivatives, I think it's just a matter of whether Ken has time.
Because all the derivatives that are supported are with respect to the coordinates and not with respect to the fields, right? Which
Yeah,
is what
I guess
you wanted
but I think that's the only key element left to like have the full processing NerpY from action to code.
That's right, that's right. And actually, I have another question, kind of following up on that, because you mentioned as you were going along that BSSN equations are already implemented in NerpyLaTex. So assuming I wanted to take a different theory of gravity, I wanted to have a different transformation, could I implement that myself, or could I base that upon what's already in NerpyLaTex? How easy or how difficult would that be?
I'm not sure. I don't know, Zach, if you want to speak to any of that. I'm.
Yeah. So, you know, I think basically what Helvy's asking is, how difficult would it be to extend the grammar and support other more generic types of operations, say, you know, something that's non-GR.
Oh, okay. So
does not obey the normal rules that we've coded up. I mean, yes, we have Einstein notation.
So we were talking about that NerpY post-Newtonian stuff before, right?
Not okay. So
just to give an example or something like that, where you had completely different notation. So I was trying to add support to parse post-Newtonian equations, and without actually changing the grammar, which of course you could go do and change stuff internally in the parser, or you could make an issue on GitHub and ask me to change and say, hey, I need this type of equation parsed. I don't have these features. Can you add support for something like this? You could do a lot of things with that srepl macro. Like I didn't show its full power here because it can get really complicated and you have to stare at it for some time, but just doing string replacements alone, you could get NerpyLaTeX to parse a lot of very, very unconventional things. I don't know if that answers the question. But
I see.
So, and this is something that we would be, so following up on Alex's comment, so this is really powerful and really cool. And these would be things that I would want to be able to do if I say, you know, I don't want Einstein's equations, but I want to have, say, additional terms in my equations of motion. Can I derive that, or even if I start with equations of motion, can I then do a 3+1 decomposition, and can I go to something like BSSN in a more flexible way, beyond what's already implemented, without having to bug you, but you know, basically knowing what the grammar is or extending the grammar.
I think if you have the 3+1 decomposition, it's easy. But if you don't have it, like going from G mu to 3+1, I don't think that's supported.
Right, because that's one of the things that I would do an extensor, and if that's something, coming back to Alex's comment, if that's something that you can do here, that would be extremely powerful.
So I think the question, Ken, is it's tied to the first question, is if instead of having the BSSN equations, you have Einstein's equations, right? You have G mu nu equals R mu nu minus half of G mu nu.
Yep.
Can you create the 3+1 decomposition? That's something like that, right?
For example,
automatically.
Yeah.
So right now, I don't think we do that.
No, that's correct. So I mean, the workflow I had in mind for NerpyLaTeX when we were developing it was basically the ability to take, you know, complicated tensorial expressions where most of, at least when it comes to BSSN, the derivation had already been done. Not starting from an action per se, but you know, the more I think about it, the more I realize, you know, it's not, I think, that large of a leap from where we are right now to being able to go from Einstein notation, so from Einstein equations to, or the Einstein-Hilbert action, if you will, to say a BSSN or something like that. I don't think it's an enormous leap, but I think the key here is, you know, the variational derivatives.
Yeah, but not only, right? So, like if I think about it, basically, for the way it is at the moment, I would have to use something else to derive the equations that I want to implement in BSSN form, or you know whatever.
Exactly. But Helby, the idea here is that, you know, you're going to have to tech, at the end of the day, you're going to have to tech that up and put it in a paper, right? So once you've teched it up, you basically just throw it in NerpyLaTeX, and it has, you know, you combine with the capabilities of NerpY, you have the immediate ability to output, do full, you know, numerical workflows from there.
And
so
it was just curiosity, because with that extension, I think you would have something even more powerful than what you have now.
You're absolutely right. Yes. Yeah. And I think that's something that would be useful for us to look into. And Ken, the term is like a very, yeah, go ahead.
Sorry, so I think for the derivation of the equation, you can use other package. So there's a Sage manifold. It's very similar to exact. So you can do 3+1 decomposition because they basically, they only have this concept of manifold, very similar to exact. So maybe you can use that and still Python, then you can maybe generate the equation, then you can use
but then it breaks the workflow a little bit, right?
Yeah.
If NerpyLaTex could support it, it would be a one-stop shop.
No, you can. I mean, you can call a package maybe.
Yeah. But that's basically just another external package to derive your BSSN equation.
Yeah.
What was the name of
this? Python, right?
Yes.
SageMath, I haven't used SageMath, you say it's called, but I haven't used it yet.
So Sage is very
Sage manifolds, right?
Yeah, Sage is very similar to Mathematica. So it also has a Sage manifold, very similar to exact.
But Sage
I suppose one idea would be to use, because this is all in a Jupyter notebook, at least how it's currently been presented, one could use the Sage package at the top to do the derivation, and then once one has the derivation, one could, if it supports output to LaTeX, for example, which would be wonderful, then that could be used as input to NerpyLaTeX, and then one could complete the workflow, at least from my understanding.
Yeah, let me write this down as a possibility that we should look into.
So since Zach is here, and my question could be a little bit mean, I don't want to ask any question of Ken, but I can ask of Zach. So initially, NerpyLaTeX was kind of sold, as far as I can tell, or promoted as being something where you can basically unparse the expressions in your paper, you get something that you can then work again with. Now then there's these additional annotations you hide in comments, so I would say this isn't quite doable anymore, because, well, I guess LaTeX is just too annoyingly flexible. But on the other hand, it now gained a lot of symbolic algebra capabilities in here, which are really, really useful. The less roughly thing that you do a lot of things. So where's the journey going? Is it going to develop eventually into a more fully fledged symbolic algebra manipulation system, maybe competing with Mathematica, Exact, or Sage manifold? Or what's the goal in the end where you want to go with it?
So with regard to the Einstein toolkit, the idea is to use the existing NerpyLaTeX numerical workflow. So for example, Ken mentioned that there's a complete NerpY tutorial notebook, Jupyter notebook on basically you go to a paper, you find the BSSN equations, evolution equations, and then you go in the NerpY, and then basically there's an interactive session that where step by step by step. Well, there's an error because we haven't defined a metric. There's an error because blah. There's an error because blah. Right? The LaTeX. The key here is LaTeX is a typesetting language. It's not there to designed to remove ambiguities. You have to remove ambiguities in order to
I'll just say something.
Make it useful for
if I had just had this equation and I just said, hey, I want this convert to SymPy, it would be impossible. Right? There's things that I have to know. This deriv.dd stuff is just stuff for transferring to NerpY, right? But for it to do this covariant derivative, it needs to know what the metric it is. It needs to know the dimension of that metric. It needs to know, there's just things I need to know ahead of time, that this K is a constant and it doesn't depend on other variables in my coordinate system. There's not taking a derivative of this, but if I was, right, just the annotations are just there to, like Zach said, resolve ambiguities in the fact that LaTeX is a typesetting language.
I have an answer to Roland's question.
And because I mean, the normal workflow instance is you start with Mathematica, you export to LaTeX, and that's that, and then you publish that, and apparently the 90% of people then delete the Mathematica notebook on their hard disk, print it, shred it, and burn the paper or something. Apparently that seems to put up. So you want something that reverses the process which you provide. So this is great.
Well, I guess kind of the way I see it, right, is what you do is if you use this to generate your code, then when you go to write your paper, you can take the input from this and just put it directly in your paper. I guess that's the way I would see this going.
The way
rather
you're
than-
supposed to do it, yeah, is instead of just putting this equation in your paper, right, you copy the entire thing with all of these commented commands, which won't render and put. So on our GitHub here, I have a link to our archive paper, and all of the equations in the paper and those examples, of course, have the NerpyLaTeX code embedded. So you could go to archive, download the source code, copy out all of our examples, put it in a Jupyter notebook or a Python script and run them and get the SymPy output. That's the idea.
Yeah, but okay, LaTeX is not my favorite way of necessarily doing math. I mean, if I'm going this direction, I would probably actually go and use either SageMath or Mathematica and then attach the Mathematica or SageMath notebook as an additional file.
Right, and if that's easy to input here, then it's super useful.
Right.
Yeah,
And
but
this one
usually you
lets me
have
do it
the
inline.
equations typeset anyway, because you're going to write your Mathematica from the typeset
Yeah.
That writes
equation, and then you can put it there and it will do it for you.
The one thing I wanted to say too is that, again, Mathematica is not free, so some people don't have access to Mathematica and stuff, which is our idea for using SymPy in the back end. But two, depending on what computer algebra system you're using, Mathematica, Maple, what have you, they all have specific notation that they came up with for how they do things. Whereas I think everybody in this field or any STEM field knows LaTeX notation. It's sort of like a nice universal math notation. And so you have that benefit of this. I wouldn't necessarily call this like a computer algebra system, but that it has that unified notation that everybody could just read. Whereas if you send somebody a Mathematica notebook and they don't know Mathematica, then they have to go and look everything up on Wolfram's documentation, right?
Well, here,
Is
you
part
know
of the
what,
idea, but
So I still need to learn something. It's not for free.
Yeah. But I think the thing we
did.
did that's nice is you don't have to read a bunch of documentation on this, because if you just try to parse this equation, you're going to get error outputs that are going to guide you into how to write these, hopefully, which is what our BSSN notebook shows. I don't know. You still do have to learn something, yes, but nothing in terms of how to typeset math, right? Just these little things to attach details to your tensors when you create
But it's
them.
not good for tensor manipulation. I think that's yeah.
And I mean, I still think it's a really good thing to
Oh
have.
yeah, yeah,
right?
absolutely, yeah. And then if we can combine the workflow, as we said before, I think this will be.
So I have another comment on people always saying that Mathematica is not free, but if you don't use the notebook, you can use, say, Jobit to attach to the mathematical engine, and it is free.
What can you say that again?
Attach what?
Attach, you can use Jobit notebook and use this mathematical engine.
Oh,
So
really?
it's totally free.
Oh.
Is it?
Yeah,
So
Yes.
that's Wolfram's script basically, or
so basically the language, the grammar is the same, and you can type in. So I have an example. So you can basically it's not Python. The back
You
is
create a
mathematical
kernel.
language. The kernel is mathematical kernel, and the engine is free.
I'd be interested in knowing more about that.
Yeah,
me too.
that sounds
I've never
really
heard about
interesting.
I've never heard of that.
Yes, it's free. I was trying to say.
No, but that
don't
sounds
say
really
it.
cool. Yeah, if you can show an example about
Sure,
this,
sure,
it'd be
sure.
great. Yeah.
I can-
Well, that's what I want to know. Is it free as in beer, or is it free as in, we'll get you later?
well, the other one is
Yeah. I've never trusted Wolfram to that extent, farther than I could throw him, and I can't throw very far. Yeah, well, I mean, I could understand it being free, but I've used Wolfram Alpha before, and I know better. It's free, but with enormous limitations. Like put in any sort of, non-trivial integral, and it'll immediately say, well, this exceeds your allotted runtime. So when they do give something for free, it's limited, and I mean, you can understand why. They're a company, and you're running it on their servers ultimately,
Right,
not
but
running it
this-
on your computer.
Leeway is talking about something that's not running on their servers, right?
No, desktop.
Okay, so I would be very curious
Sure,
to see
sure, of
how
course,
this
of
is
course.
done. Maybe
Yeah,
in the
I also-
afternoon or tomorrow.
yeah.
If you're
Of course,
here.
of course.
If you could put like a link in the chat or something, that would be really awesome.
Yeah, I can.
maybe also in the notes document.
Yes.
Yes, but we can, once he adds it to the chat, we can put it in.
Yeah,
Yeah.
yeah. Just make sure to edit.
Yeah,
Yeah.
Okay,
because it's a little bit obvious. I get the chat messages eventually, but
Mm.
they end up somewhere on my hard disk.
That way someone with a more sophisticated Mathematica notebook could try it out and see if it works.
Yeah, yeah. No, but I would be very curious because in 2 weeks' time I'm supposed to lecture in our community summer school, and I wanted to do this usual, how do I derive the ADM and BSSN equations. kind of thing. And at the moment, I have that as a Mathematica plus exact notebook. But if there's a way to do it this way, it would be really cool.
Helvi, do you have a copy of that notebook that you've been that wonderful? It uses exact extensor notebook for deriving BSSN.
So I have that for BSSN privately. I only have the ADM derivation public, and we should actually have that in our tool, right?
There's the one you presented in 2021.
That's right. This is my standard ADM derivation. The private one, I also have a BSSN derivation. But yeah, if you're interested in that, I'm happy to share.
Yeah, I mean, I'd like to just stare at it and see where any gaps exist in NerpyLaTeX, where it would be useful to fill in. You see what I mean? Yeah, that's sort of what I like to see, you know.
So the other thing that Levi was saying, I think I would start with trying to see if I can adopt my ADM decomposition notebook to that. Maybe. So if you, Levi, if you want to give maybe a half an hour or so overview, either in the afternoon or tomorrow.
About what? Sorry.
What you were saying, to combine the Jupyter with the Mathematica front end?
Yeah.
Yeah.
So, Ken, I was just looking at, I just checked out your source code, and I was just sort of ramping through it a little bit. So, NerpyLaTex does not import NerPy anywhere, right?
Nope. It's a separate package.
There's no NerPy. Got it. It's a completely standalone package.
Yep.
Okay.
Because that's the thing. You have these two workflows. I could do Analytic or Numeric and then pass Numeric in some type of workflow pipeline to something like NerpyPlus. Plus. But if you wanted to do analytic calculations, then I had to make it standalone. You don't have to download the whole NerPy tutorial.
Right.
Yeah, the dependency is NerPy depends on NerpyLaTeX, but not vice versa.